Another important principle after Hamilton's principle or modified Hamilton's principle is the principle of list action. It is somewhat like Hamilton's principle but more general because the variation of the path that we considered earlier, in this principle the variations are of more general type. We'll see that. First, we define a quantity called abbreviated action. This is defined to be generalized momenta times generalized velocities. There is a sum over j, so momentum times corresponding velocity, and after taking the sum, integrated over time from t1 to t2. Now, the statement of this principle of list action says that if we consider conservative systems with Hamiltonian equal to T plus V, the kinetic energy plus potential energy equal to constant. For such systems, the variation of the abbreviated action about the true path is 0. And we mentioned earlier that when we were looking at the Lagrangian dynamics, we could define a complete description. We could give a complete description of a system using generalized coordinates and their derivatives. So in general, the generalized coordinate can describe a system where it is and how fast it's moving. So we used to call the collection of Q to be the configuration space. Now in the Hamiltonian dynamics, the generalized momenta and generalized coordinate both enjoy the status of coordinate. So we need 2n set of quantities P's and Q's to denote the physical status of a system, and we call it like a phase space. So a particle which is actually moving, let's say we have a 1D particle, it's going from this point to another point. So at every point of the journey it has some momentum, so at every position it has some momentum. Okay. So the journey of a particle is can be defined in a phase space. The phase space is usually defined by the Q and P. It could be multidimensional, of course. I am considering only one-dimensional system, but if you have more Q's and more P's, it would be difficult to draw. But you can imagine in a multidimensional space, the particle dynamics is essentially from one point to another. For each Q, we'll have for each set of Q's, we'll have a well-defined set of P's. So variation in the phase space about the true path will result in the delta A to be 0. Okay. So this is essentially the statement. But what is new here is what we call delta variation. This is unlike the previous variation. How so? Previously, we were looking at as a function of time the generalized coordinate which starts from this point and ends at this point. Suppose this is the true path, and we were looking at a variation. Okay. The variation vanishes at the end point, but otherwise at every instant t there is a difference from the true path. We defined it parametrically by, for j generalized coordinate, we defined it's a function of t and alpha, where that this is the true path t0 plus alpha times the variation. So as such, this arrow downward is basically this quantity, and qt0 is this point, and this particular point is qt alpha. Okay, that is how we created the variations in the path. We have already seen that. Now in delta variation, we will allow the endpoints to move. So if we are doing this in the phase space, then let's suppose this is t1 at this point, it starts, follows the true path, at t2 it stops there. In phase space, we are considering another path like this where the motion starts at t1 plus delta t, ends at t2 plus delta t, t1 plus delta t1, and then t2 plus delta t2. And as we see, it is different. The q's and p's are shifted, so endpoint could be different from the starting point. Or if we draw this entirely in terms of q's, then the picture is simpler. Suppose this is the original path and this is a variation. So for this q, at this particular time, this variation is like a virtual displacement, does not involve time. So this is like delta q. Now at this point, how much we shift, one can calculate, assuming they are parallel for very short numbers, we can calculate the q dot, multiply with delta t. If we do that, then we get this particular height. So this distance plus the change, that gives you the total variation of q. So this delta variation involves a part which is coming from time. So this is more like a real displacement. Just like we demanded in our earlier variation that delta q vanishes at t1 and at t2, similarly this time we will demand delta q, for here the delta means this type of delta, capital delta, it vanishes at t1 and t2. Okay, this is with the old variation, and this one is called delta variation. Okay. Now another important thing that we must remember, that earlier often we interchange these two operations, the taking delta operation and the time derivative. This was completely equivalent to ddt and delta. In fact, this operation, we try to do this using the parameter partial derivative. So for us it looks like for a pure function of time and alpha. So if we have function which is a function of t's and alphas, then this holds simply because the alpha is not a function of time. Okay, so these two derivatives were interchangeable. However, when you consider delta variation, this delta of ddt is not equal to ddt of delta. So we will be careful with this. We must not just blindly interchange the order. Otherwise, delta acts like just a differential. So for example, we have a function which is a function of q and t, then delta f can be written using the chain rule to be simple. And then remember, the delta variation of qj is our old variation, and the velocity times delta t. So if this holds, then we can replace delta qj here to get remember the sum, we have sum over j. Now this quantity we denote it as the variation of f not involving time, and this quantity it's nothing but total time derivative of f, so it's like df dt, or one can simply use the shorthand notation f dot delta t. So this is one important result. I mean, of course, we know we got it for q's, but we are showing that this holds for any general function of q's. Okay. The next part, what we would like to do is to actually carry out the mathematics for our defined abbreviated action A. So A, we defined this to be this. Now, you may recall that we have Hamiltonian to be, these are our definition. So Pj Qj dot in terms of L and H is simply the sum of the two. But then we assumed that H is constant. So this integral, it then gives us simple. Okay. As such, so when we look at the delta variation of A, this should be equal to delta variation of the action. By action I mean the Lagrangian integrated over time from t1 to t2 action integral, and we will have h delta t2 delta t1. What it means is the h is constant, so we are considering all paths for which h is constant, and this delta t2 and delta t1 are variations at the endpoint. We mentioned that now the endpoints are, we are allowed to vary them. Okay. So this of course can also be written as h delta t evaluated at the endpoint, where delta t takes just the value delta t1 and delta t2. Okay. But you remember we got an important result here, that delta f is the variation of f plus the total time derivative times delta t. We use that for this integral. So which means we can write for the delta variation of the action integral to be the regular variation of that action integral plus ddt of that integral LDT times delta t evaluated at t1 and t2. But then ddt of that integral, by definition this is L. So what we have is just L delta t. L delta t, and that gives us, okay, maybe we will leave it as it is, and that gives us L delta t, t1 and t2. Okay. Now what about this quantity? This we have done it already, so it is not difficult. We know that the variation of this integral, essentially the variation comes from only the Lagrangian part, and that would be now. You would say, I mean, we did not do anything of that kind. What we did is we had an integral I, which is a function of alpha, and we had L, which is evaluated over Q. Q's are function of alpha, and we had this integral. And from there, what we were trying to do is we calculated this and we pushed alpha in, and we got something like del L del Qj del Qj del alpha plus del L del Qj dot del Qj dot del alpha. We got something like this. Now, that's absolutely correct. No issues. If we multiply this quantity by d alpha, so that means d alpha goes in everywhere, and we identify these to be the delta Qj, and this is like a delta Qj dot. Then you will identify this also to be okay. Then what I wrote in the first line has just a simple correspondence to what we have been doing earlier, except the notation is now slightly different, but that is okay. I mean, like nothing new there. So we considered, we were considering a Hamiltonian which is conserved, and of course for such systems the Euler-Lagrange equation is also valid for such system. So we are considering the variation about the true path. So on the true path, this is always correct that ddt of del L del Qj dot is equal to del L del Qj. That always holds. And our variation is about the true path. So we are allowed to use this substitution here. So what we get from this expression, we will separate it out. Basically what we have is T1 to T2, we have ddt of del L del Qj dot plus that's it. This is actually easy, because if these two terms are combined, what we have essentially is the total time derivative of del L del Qj dot del Qj. That's it. And that gives us, remember, this is Pj del L del Qj dot. So we have Pj delta Qj Pj delta Qj evaluated at T1 and T2. That's it. Right? Yeah. Now, delta Qj is connected to the delta, I mean, delta Qj means here the regular variation that is connected to the delta variation of Qj as this. We substitute that here to get now, the first term is 0, simply because we demanded that delta Qj must vanish at the end point. Just like our old variation, we were demanding that this should vanish at T1 and T2 at the end point. Similarly, here we are considering the delta variation to vanish. So if this is 0, then what we have is, after this long calculation, that's all we have. that Pj Qj dot delta T evaluated at T1 and T2 and with this negative sign. This is equal to our delta A. Not delta A, sorry. This is equal to the this. Now, if we substitute that to our original equation, which was the delta variation of A was given by and we substitute it here to get but this is 0 simply because you see, I mean, minus Pj Qj dot, there should be a dot here, yeah, Pj Qj dot plus L, that gives you minus H, so that cancels and eventually we get 0. So that means all the conditions that we assumed, which are the delta variation of Q's must vanish. So I mean, we demanded that this was one condition. The other condition was the Hamiltonian is conserved and we are looking at variation over the true path on which the Euler-Lagrange equation holds. So if we apply all three, then we arrive at delta A to be 0. So which means that the delta variation of A, where A is given by the abbreviated action, its variation over the true path vanishes. At a first glance, it does not look like anything special, but it has quite a few application. And this is when we look at those applications, we'll realize the power of it. For example, consider a case where the potential is constant. Okay, so V is constant. So if V is constant, then Pj Qj dot is equal to H plus L, which is equal to twice T. V anyway drops up. So this will also be constant. After all, H is constant. So if V is constant, then T is constant. If all of them are constant, then this what we have is the delta variation of A would be equal to the variation of this is T dt, but then T is constant, so no point talking about its variation. So that gives us a simple time integral from T1 to T2. Its variation should be 0. So that means that's all we have. So what does it mean? It means that the true path must be the shortest path, because a shortest path is one extremum. Of course, you might say, why not the longest path? Yeah, that is also correct. I mean, one can have the longest path. I'll show you an example shortly, but let's make the statement clear. If we have a particle for which the total energy is constant and the potential is also constant, that means the kinetic energy is constant, then the true path would be one which is extremum with respect to variation in time. So the true path takes shortest time. I mean, what about the longest? I mean, after all, the extremum condition we are talking about. Okay, first let's say we are considering about a particle going from point A to point B in a plane. The longest paths are many. I mean, it can go to infinity and then come back. Definitely such paths are not physical. And this straight line looks like the the correct path, because and also it happens to be the shortest. I mean, we do not know whether the longest one gives any meaningful physical result here. But if you have a sphere and you want to go from point A to point B with constant speed, then this is definitely one possibility. The other possibility is start moving the other way and go around the sphere and come back. So such lines are basically essentially called geodesics. The geodesics are the Fermat's principle. These are basically the least time path which gives you least time or maximum time. So in this case, the part of the greatest, the part of the other part of the circle, I mean that is also one possibility, and this is other possibility. So both are combined to give you the geodesic. Okay. So Fermat's principles also used in optics. I mean, in optics, the speed is constant. So there you might say this is a principle of least time, can be directly applied. Okay. But then there is a straightforward extension to Fermat's principle. After all, if this equation holds that the variation of dt 0, then one can multiply the speed and get something like b dt, which is equal to the elementary path length ds to be 0, and that gives you the principle of least path. So shortest path or the maximum path is the one, I mean path which takes the minimum time or maximum time, and the path which is shortest or longest, both are equivalent as long as the particle is moving with a fixed speed or kinetic energy is fixed. So this more or less concludes our discussion on the delta variation. So in summary, delta variation is a variation where we consider not just virtual displacement kind of thing, we also consider how it is changing with time. So these sort of variations are more general. So in a way, this principle of least action, I mean, although we did it with abbreviated action, but it's okay. I mean, we still call it principle of least action. Maupertuis gave this principle long back, I think 1750s. The principle is quite powerful because compared to the Hamilton's principle, where we kept the endpoint fixed, moreover, not just endpoint fixed, we kept the end times fixed. But in the principle of least action, end times are allowed to vary. And we found that even under that condition, the abbreviated action gives us an extremum condition for the correct path of the system. The limitation of this is, again, we did it for a conserved Hamiltonian, conserved system, which is definitely not most general case. But then for that, we already have other principles.